Audio, video. No, audio is okay. Then they also see me. So now everything is set with the Zoom session. Okay. Okay, so first, thanks a lot for giving me the opportunity to present our work here, which is actually a work with one of the organizers of this meeting, Odette. But it was also mainly a work of two very good PG students in my group, Hannes Weisbrich and Raphael Klees, who left in the meantime already some while ago, partially. But I still really enjoyed working with them. So it's about fractional states of matter in a superconducting system, fractional transconductance. Basically, I would like to repeat a bit some basic things because this is about superconducting system, which is not so much the topic of this workshop otherwise, and also a fraction or quantized transport. So I would like to repeat the main things here. So is it okay? You see me? You see my screen? Okay, perfect. Okay, let me start with a basic reminder of the quantum Hall effect, which appears in a two-dimensional electron gas. See the pointer here? Yes. In a perpendicular magnetic field where the current is going in one direction and the voltage appears in the other direction. And then it turns out that this voltage or the corresponding resistance is quantized in units of a universal constant h over e squared, just consisting of natural constants and divided by some integer number. And this is kind of quite surprising, I would say, because this is a very high accuracy, which usually does not appear in solid state systems of any kind of response function. So the main reason for this is that the system is gapped in these Landau levels and these macroscopic degenerate levels. Therefore, they are kind of very stable when a full level is filled. To understand the quantization, one can follow this topological argument by Laughlin, which was later kind of around the same time solidified by Saulis and others. That where you understand that which can be understood in the following way: if the two-dimensional electron gas is wrapped around a cylinder and I change the flux inside, it turns out that the states are periodic. But what happens if I change the flux by an integer number in terms of the flux quantum? I exactly transport one electron to the other side, and this means I transport one electron per flux quantum, and with this relation of the kind of time derivative of the flux is related to a voltage, I can basically understand that the current is therefore quantized in terms of this universal constant E squared over H. So in this adiabatic pumping argument, I can understand the quantization. And it was also shown then by Saulis and others that this is actually a topological origin, which is why it's actually sensitive to disorder and all this stuff, which is actually present in this samples. Actually, we know by now that you actually need disorder to stabilize these plateaus. Okay, so it's a kind of very interesting observation and kind of had a lot of consequences until today with the advent of topological insulators and things like this, which are studied nowadays. Okay, then it was found that in certain samples of actually high quality, they observed fractions of this conductance, like in this form here, where nu, okay, is an integer number. Actually, it's an odd integer in this case. It turned out that this was explained, interestingly, by Laughlin, by essentially writing down the almost exact wave function of the systems, which may be interesting to note that you just find in one state solution of the Schrödinger equation, and you can get the Nobel Prize for it. And it turns out that the point is that due to interactions, these states split up, and you have an actually degenerate ground state. And now, using again a similar pumping argument, you will see that you, by changing one flux quantum, you do not go back to the same state, but you go in some sense to the other state, then to the other state. And then in this case, if you change your flux by 3 flux quanta, you pump 1 electron through the sample, and this in turn means that you, so to say, have in this argument, in this pumping argument, you have this number of flux quanta here as a fraction in the conductance. And this basically can also be viewed in this way, where you go along such a manifold, which is kind of here artificially kind of enhanced in energy, and you stay in that state. And this state is in some sense in 6 pi periodic in this case now for filling fraction filling fraction 1/3. Okay. Now, this is all kind of well known in semiconductor systems. I want to talk about superconducting systems and topology and quantized conductance. So this is probably rather exotic here in the context of this this conference. So I would like to introduce this by reminding or kind of explaining the finding of this theoretical paper by Nazarov's group in 2016. They basically suggested to use multi-terminal superconducting junctions. So what is a superconducting multi-terminal system? This is a system which consists of a number of superconductors, like in this case, 4 terminals for superconductors, and the superconductors are characterized by a macroscopic phase. And then it turns out that there are bound states. These are, so to say, Bogoliubov solutions of the Bogoliubov-Dejean equations, if you want. So-called Andreev bound states are formed in this region, and the energy of these bound states depend on the phase differences. So this is the origin of the Josephson effect, actually. And it turns out that if I have more than one phase difference, of course, I can plot a phase difference in such a artificial synthetic Brillouin zone, and therefore can play the games I know from solid state materials, where these are K vectors with introducing the synthetic dimensions formed by these phases. And then it turned out that I can create in such a system zero crossings, which are called Y nodes. When a Y node appears, zero crossing, I can have a change in the topology of the system. In that work, they kind of looked at randomly generated scattering matrix, and from time to time, they found a zero crossing like here. And then it turns out that this kind of results in a change in the topology and a change so in the Chern number. I will explain or show you in a second what. So this is how this Y nodes are distributed here in the Brillouin zone in that case. Now one can now continue with this or kind of take over this pumping argument from the quantum Hall effect in this case, and one finds that the current, so can also define a kind of Hall conductance, synthetic Hall conductance, by measuring current in one branch by applying a voltage to another branch. So this is like X and Y in the quantum Hall effect. Now it's terminal 1 and terminal 2 here in the phases. And then one can show that the flux, changing the phase corresponds to applying a small voltage. This is called the second Josephson relation. And then the average, so the current, the instantaneous current is given by there's this number here, or this expression here, which contains actually the Berry curvature of this state in terms of this phase parameters. And if I average this now over time and phases, basically I obtain this integral over the Berry curvature, which is a Chern number, and this, according to this exactly similar argument as before, leads to conductance, which is transconductance, which is quantized in terms of the fundamental quantum here is 4e²/h, because we talk about Hooper pairs times the Chern number of the ground state. Now, this has been proposed, and I will say in a second where experiments are, or some experiments are. We have now also worked on this. I just quickly mentioned a lot of works we did in this case. We were working with slightly different approach where we kind of engineer systems like this one, which has 4 terminals and some kind of single level quantum dot, so far without interactions here, which shows topological phase. One can do it with 3 terminals and adding a flux here. One can look at chains, which we did here, which also have topological phases. Finally, we found kind of the simplest instances is such a system with a double dot, which is connected here to 4 superconducting terminals. So they all have topological phases, and we studied them a lot. And I don't want to go into any details here because I want to target something else in this talk. Experimental status, one experimental group working on this is a group of Fabrizio Nichele at IBM Zurich, and we kind of worked with them. So they make such structures, and you see an example here on the next slide. So this is an experiment in a 2-dimensional electron gas semiconductor, and these are superconductors. These are loops which are controlled by current lines so that you can control all the phases individually. So it's kind of quite a masterpiece to kind of create these structures. And here it shows us a spectroscopy of such a curve. So it depends on 2 phases in that case. And this is the kind of the status, creating this and detecting this by spectroscopy. And this is all I want to say about this just topological superconducting structures here. Now I want to come to the question. I have told you now that such systems show a quantized transconductance, and then some kind of obvious question is, can we also have a fractional conductance in such systems? And that's where we kind of started to think about. We looked at a slightly different system, but there's much of the physics is very similar. Instead of Andreev states, we look at Josephson circuits. I quickly again introduce them here. I think they were already mentioned yesterday in some sense in the talk by Moshe Goldstein, I think. Yeah, right. The basic building blocks here are Josephson junctions, which are, so to say, connect 2 superconductors with such a junction. There can be, one can write an effective Hamiltonian here, where a Cooper pair is transferred from one side to the other. There's a dual effect, so to say, that if you have a superconductor disconnected, or only connected through junctions to the rest, it will have a finite size, and therefore the finite, if I put another excess Cooper pair there, it will cost an extra energy called the charging energy. And then I have this kind of relation that depending on the excess number of Cooper pairs, I have a charging energy. And then these 2 quantities, the phase and the charge, are here conjugate quantities. And this has been much of the subject of studies in the 90s by various people. And for those who are interested, you can have a look in this review article, which is actually from 1992, but was put on the archive in 2005. So this kind of systems can play similar we can play similar games. So, for example, it was suggested to make such a system. Here you see kind of an effective picture. So the dots are the superconducting islands, the crosses are the Josephson junctions. Here you have 2 voltages, voltage Y and X, and you have a third ground here. In this case, one can engineer this structure such that it also has such Y nodes. And in that case, one can kind of bring it in a situation where the conductance, the transconductance here is again quantized in units of 4e² times some Chern number, which is given by the ground state of this system. And we asked ourselves, can we simulate fractional physics here? And that's what we found. So we looked at such a system. This is an array of junctions. And so there is a a longitudinal voltage, if you want, which is called Vy, and a transverse voltage is a time-dependent flux threading these loops. And there's kind of a control parameter, is an offset flux between each of these loops. And so each of these dots is a junction again, and we assume that all these fluxes can be controlled individually. Maybe it's not so easy, but that's what we look at. And then we basically, so we can look at a case where this flux is exactly varied by such an integer number, and then we kind of write down the full Hamiltonian. I probably don't go into details here. One can basically write down this Hamiltonian. There are lots of capacitances here which I have not drawn, and in principle there are gate voltages which can be controlled, but we don't. They're not shown here. And this system, this is very complex. It has many states because n can be for each junction, n can be any number. And one can, so to say, control it and bring it into a form where we, or kind of put the, change the parameters such that one has a effectively low energy, small dimensional Hilbert space, which consists of just a single excess Cooper pair in the whole junction, in the whole array, or 0 Cooper pairs. So we have basically the number of states we have is exactly the number of islands plus 1. And in this way, you can already imagine that this is, of course, good for kind of transporting single Cooper pairs, because you want to kind of transport one Cooper pair through the island, and it exits on one side, and you start with 0 again to enter it on the left side. So that's then you have obtain an effective Hamiltonian, which is now much simpler because it has only this state number of the island, the number of islands, and this state, and then we basically, what we did, we changed these phases here with time, right? That's kind of the voltages, and then numerically integrate the Schrödinger equation, then first of all we kind of look at the junctions or the kind of states, and using certain parameters which have to be engineered, we find such a spectrum where we have this low energy band here, which has states which are in some sense which are 6 pi periodic in this case. So we see that this is exactly what we want for a fractional transport. So we have this multiple 2 pi periodic states. Of course, there are several of those, like in the other case. And now we study adiabatic transport, and we also, of course, need that this state has a non-integer non-zero Chern number to give a topological transport. Okay, this shows again the band structure. Now we simulated this for 3, 6, and 9 islands, and here you basically see the instant current as a function of time, and as a kind of after some initial time, it kind of saturates on a certain integer value here, or in this case, at n equals 3. It's just an integer value, right? So it's 4e squared over h, the conductance here. But for 6 junctions, for example, we have 1/2 of this transconductance quantum of 4e squared over h divided by 2. And for n equal 9, we reach here this 1/3 quantization condition. So we have a situation where we have this quantized conductance, but now the question is, how is this actually a stable phase? And this we simulated in the next picture. Now we change this flux not by a definite amount, but this is our control parameter. This is a control parameter, this offset flux here. And for integer numbers of this integer in this sense, or that it's 2 pi divided by n or 4 pi divided by n, we have an exact situation where the states are, there's a kind of one state which is transported through the island, or we have 2 states, and these 2 states, to transport a full Cooper pair through the island, we have to change the flux by 4 pi, or the voltage by the voltage flux, or by 2 pi or by 6 pi. And then we can simulate this as a function of this continuous parameter, and we find these plateaus in the conductance defined in the way I just described it at integer values, or at integer at certain fractions of the conductance quantum, and they are stable around this point in the middle. In the middle, there's always a point where we have the exact situation which we want, but it's important to see that it's kind of stable around this point. And why is it stable? Actually, this can be understood in the following picture. The point is that if the flux is not exactly an integer, like this one, there's a certain gap in this now in this kind of case of two states here, and in this case we do not want to stay in the ground state here, so we don't want to have really truly adiabatic transport, but we want to stay in this state, which is kind of, so we want to go up here through this gap and stay in this state and then go down here. And this means we have to go with a finite speed. And then we have some kind of Landau-Zener tunneling to go, to jump here with a high probability to end up here. And then we have the same probability to go down again. If this speed is just enough, then we are in the right business. But of course, we should not be too fast, because if we are too fast, we might go up to higher states, which are not shown here. So there's a certain region in the voltage where we have a quantized plateau in this case. So which is exactly like I say, the voltage has between this energy and smaller than the energy to the next levels, and that's why this kind of quantized conductance is stabilized by this non-adiabatic Cooper pair transfer here in this voltage regime. All right, so that's the main result here. So we find this, I just show it again. So we find this quantized, theoretically find this quantized fractional conductance plateaus in this superconducting system. Okay, then we studied what happens to if we add this order. Of course, if we change basically these offset fluxes by some random amount and vary this, and then well, we basically with some statistical analysis of the transconductance, and in some sense we don't get these integer values anymore if this variation is too large, but again, for a certain region it is still valid. Okay, then okay, maybe I go to this slide before I finish. What is important here is so to kind of show you that it's really important to have interactions here, so which means a finite charging energy. So the right side, this is the picture I have now shown to you, and this was plotted in the limit where the charging energy is much larger than the Josephson energy, which is a bit difficult to achieve in practice, but if you make it smaller, then what happens is, so here we have these nice bands there, but if you make the charging energy smaller, more and more states come from, so to say, above down. Yeah, so these are the states with this is n equal 9. So these are the 9 states with 1 Cooper pair per island or 0 Cooper pairs, and now comes the states which have 2 Cooper pairs in the system. They kind of come down, and if you make the charging energy smaller, more and more states come down, and then obviously this kind of assumption that we stay in this low energy manifold, if we change the parameter, is not fulfilled anymore, and therefore the conductance, the quantized conductance will vanish. All right, so that brings me basically to the summary. I just kind of showed you this work here, which appeared last year in Physical Review Research, that we can engineer such a Josephson junction array to show a fractional transconductance. And if you're interested in all the papers we have on this kind of superconducting topological systems, you can take a photograph of this, or you go to our webpage. And with this, I thank you for your attention. Well, in our case, this order is okay. And I think in the quantum Hall effect, at least the picture I have for the integer quantum Hall effect, to have a plateau of a certain size, you need to fix to kind of pin the chemical potential somewhere in this kind of localized states, right? And that's why you have a certain plateau, because you change the chemical potential, and that's why you have a finite plateau. In the fractional state, I understood that you need a certain, it needs to be more clean, right? But if it's too clean, if it's completely clean, you basically have you don't see the plateaus anymore in the fractional state. So in our case, I think the mechanism is differently, because we have this non-adiabatic transport which stabilizes the plateaus. So it's not this order which stabilizes. Maybe you can view it as yeah, no, I think that's the case. So it's not really that this order is necessary in our case. And I think the reason is that we do not have a chemical potential in our system, right? Because effectively we have, in the end, once we have reduced our Hamiltonian, we have like a single particle Hamiltonian in a certain subspace of the Hilbert space. So we do not really have a chemical potential. And I haven't thought about translating this into the language of chemical potential. Maybe one can do this even now.
The one at 1/4 is more or less still there, and then it's very hard to see in further.
There are no further ones in this case, because this is, so the point is, this is for n equal 18. And okay, in principle, there could be one for 1/6. But you see that in that case, the gaps become kind of smaller. And in that sense, they are unstable. But for example, going from, for example, this is in the last slide I took, this is the one for n equal 12. And then you basically, you can almost not see the 1/4 plateau anymore. So if you make them longer, certain plateaus become, kind of more pronounced. But we consider a finite length. Yeah, that's why we so to say, they become then invisible. Yeah. Well, it's a bit complicated because this conductance, it is true like this, yes. So, but the conductance is a matrix, because all these things are, even if they are only coupled like this, of course, the charge, so to say, influences all of this. But in some sense, yes, we assume that you can control the voltage on each island separately, but I think that's possible. No, the charge offsets are fixed. The charge offsets are fixed. We change the flux, but for example, the flux changes in a linear fashion. So it could be a linear gradient in a magnetic field, for example. So the true challenge is to make junctions with such a large charging energy. This is, I think, the most difficult thing, experimentally. Okay.